Okay. Welcome back after lunch. The next talk here, you might recall, those of you who had been to previous conferences here, that I've been talking about a killer app that I'm wishing for that could make APL famous and interesting. And I mean, definitely the Cosmos application that's helping people visualize data mining into vast amounts of data is one contender for that. Paul is not going to show you the application. You've seen that a number of times before, but it's now starting to get serious, and the data amounts are starting to grow. So some performance improvements was required, and I think Paul is going to talk to us about that. Welcome.
Okay, well, welcome to Deerfield. It's nice outside, it's cold in here, but it's a little bit warmer up here, so I'm all right. My name's Paul Grosvenor from Optima Systems UK. I'm the managing director, and we've been working with APL and Dyalog, and many of you here for a long time now. Just a brief bit of history. We started off primarily working with financial data and pension, office automation, things of that nature. And about 2.5 years ago, I was talking to a friend of mine, somebody I'd been speaking to and working with probably 15 years ago, in fact, about the possibility of taking some of our very old workspaces and converting them over to allow pharma companies to investigate their data, visualize their data. And we soon came to the conclusion that, in fact, the world had moved on, the volumes of data had grown exponentially, and we would benefit from a complete rewrite of all the original systems we started with. So we started with pretty much a clean sheet of paper, and our aim was to be able to take a chunk of data, a big chunk of data in all likelihood, and visualize it, look at it in different ways. So that immediately gave us some problems, and the problems have grown over the last 2.5 years. The first thing is that we have, as I've said, a huge amount of data. One of the clients we were talking to a couple of months ago, when we asked them, how much data have you got to look at? They said, well, we don't actually know, but we think we've got about 568 terabytes stored in a variety of different databases all over the world, different formats, different styles, different everything. And their challenge was to try and somehow make sense of it. Needless to say, as yet, we haven't made any sense of it whatsoever, but we do know that it's coming around the corner and there's a lot of data for us to churn around. Certainly more data than we can fit in memory in one go. The way the pharma companies tend to work when they're looking at their data, they work in a very sort of traditional way. They're using tools we're all familiar with. Excel, quite often, is one of the tools they use a lot. So when they're looking at data, it's very much two-dimensional, or maybe a three-dimensional spreadsheet, something of that nature. And they're using all the tools, MathCAD, SAS, and SPSS, tools of that nature, to run the analytics. The other problem they have is typically they'll start from an assumption. They'll make an assumption about the data, what's causing an ailment, or what isn't causing an ailment, and they will then take a snapshot of various pieces of data from their data sources, and they'll try and make their assumption fit with the data. And that can be a very long process, and quite often leads to an assumption that's wrong. So it's very much a trial and error sort of investigation the whole time. The data itself is protected under all sorts of international laws, so even getting hold of the data, being able to look at the data, causes problems of its own, and we have all sorts of data standards we have to adopt and apply to allow us to just look at it. And as I've just said with this customer previously, a lot of the data sets we have to work with are not single databases. They are multiple data sets stored all over the place. And they often have a federated view whereby they have some sort of top-level SQL umbrella, which fires off inquiries all over the place to gather information together to form the snapshot that they happen to be interested in at the time. So our system is designed to sit on top of all that. So our problems are straight away to assemble the data and then try and work with it in a sensible time frame. So if I just talk just a little bit about Cosmos, I'm not going to do a demo of Cosmos itself, not today. But basically, it's written in APL. All the back office stuff, all the server stuff is all APL. As I said, it's designed to be a data visualization tool. It's not strictly a data analysis tool, although there are some analytical functions built into it. It's a top-down view, so our aim is to allow the system to sit somewhere above all this information, this data lake, and allow the researcher to probe, drill, mine, whatever you want to call it, and investigate the data in some sort of sensible way, but also, as I said, in a sensible time frame. One of the people we've been demoing the system to described the Cosmos system overall as a thesis generator. That is to say, it allows the researcher with little or no preconceived ideas to sit down with the information and play with it in a very nice sort of APL-y sort of way. They can play with the data, they can maybe come up with assumptions or some thoughts, considerations, which may or may not prove to be correct, but they can do it much, much faster. And that's really the whole point of the system as a whole. Currently, we're marketing heavily in America, and we're targeting electronic medical records, EMRs, primarily because there's a lot of money in the pharma industry at the moment. There's a lot of work going on in various categories of disease, such as diabetes, cancer, schizophrenia, for example. And a lot of work going on. A lot of data has already been collected. And this is the sort of stuff that we want to try and pull together, if we can, and look at it overall. So rather than saying we'll just look at cancer data or diabetes data, we're trying to pull the two together and see what patterns there might be between cancer and diabetes, for example. And within the system, we have built in some pre-canned analyses which are common and often required. So things like survivability, the application of a drug to a particular, within a treatment, how beneficial is it? How much longer life expectancy do they get, or how much is someone's life improved by taking this drug? And then we can overlay that with costs and times and all the rest of it to give a much better picture of what's going on. That's the game. So, as I said, we started this about 2.5 years ago, roughly. We did the usual APL thing, dived in, wrote code, played around in the session, and we came up with something like what you're seeing on the screen now. At the front end, we've got a client. As it happened, we chose to use a Flash front end, and the Flash on the client machine communicates to our servers at the back, which is that sort of blue box over here. At the front end of the server, we have my server running, which Morten and co have already talked about so far this week. And the my server basically receives the request, whatever that request might be, passes it over to a Windows 13.2 64-bit workspace, and it churns data. The one thing we did add quite early on was what I'm calling here a cache controller, which is a very simplistic way of looking at what's been asked for and seeing whether it had been asked for before. Because if it had, the likelihood is that the results of the previous request were already held on the system. So, if you like, the very first performance improvement we made was by adding this cache, semi-intelligently looking at what's being asked for, asking itself, has it been asked before, do we have those results, and then taking the results and passing them back. Now, in the case where we get a clean hit, so somebody might say, well, I'm interested in somebody or a group of people aged 65 and above, that sort of question is very likely to have been asked before. The answers would already be in the system, and we can turn around that much, much faster. As a separate process down the bottom there, we have various data sources. There's probably about 9 different sources we typically read in. We have a separate workspace which does the importation and creating our data in a format that we like, and that passes it back up into our main system. So that's where we started, and it worked fine to a point. We were limited by workspace memory. We only were really using a single core or a single processor. And at the time when we were using this, the number of records was relatively small, probably tens of thousands, or in a few cases, hundreds of thousands. So most of the data we were interested in, we could fit inside memory, and the APL workspace handled it perfectly adequately. But nevertheless, as time has progressed, the complexity of the inquiry, the amount of data we're playing with has grown, and that model has now become very much outdated and is no longer suitable for what we want to try and do. So for those of you who've seen Cosmos before, just as a memory jogger, that's the sort of what it looks like. If you've not seen it before, that's what it looks like. I'm not going to go into any great detail about this, just to say that the yellow dot in the middle represents your patient cohort, the group of patients, which could be, in this particular case, I don't know, 50 or 60 million patient records. And the blue nodes around it, connected with lines, are indicating, I think it's drugs in actual fact. No, it's not. It's disease. And the disease is related to that cohort of patients. And we're seeing here the top, I don't know, 20 diseases applicable to that data set. And the idea is you can open up these nodes further and you can build up a big sort of Cosmos-type graph of the universe and start seeing how the data relates from one piece to the next. We can change line thicknesses, line styles, all those sort of things to indicate severity or importance, or simply just the counts. So there's a lot we can do with the system. So that's just an aide-memoir. That's what it looks like at the client side. So if we just fast forward a little bit and think about today and the problems we have, it very quickly came to light talking to some of the bigger pharma companies. One of the first things they said was, how scalable is your solution? Because it's all very well us in the lab having a couple of people playing with this tool, but they're talking about maybe doctors or their researchers or even their managers looking at all the data at the same time. So they want to know that the system can be scaled up to have a large number of users running a large number of complex inquiries, looking at a large amount of data all at the same time. So we've had to start now thinking very seriously about making this into a proper, real commercial product that will stand that sort of impact. The next thing that's come to light very quickly is security. We had a security workshop on Sunday, which was very useful. But one of our big customers, they gave me a security questionnaire, and it was no joke, about that thick, of all their protocols and things that they needed to know about before they would allow us to even look at their data. And it opened up a whole bag of worms as far as we're concerned, because, you know, as I'm sure many of you here are aware, you know, we tend to work for our customers, and our customers just want stuff. They want it quickly. They're not particularly interested in what goes on behind in the security. But it's becoming an increasingly important part of what we're delivering and how we're doing it. So security has potentially performance issues. We have to look and think about encryption, security of data transport, how we get the data in, how we store it, where we store it. In some cases, the data can't even leave the shores of America, has to stay in America. So we've got servers now. Actually, they're actually somewhere in Florida. I don't know where, but they're in Florida somewhere for some of the medical data. So we can process it in London, but we can't actually hold the data outside of the US. And the same would apply typically for UK data. We can process it in the UK if we can get our hands on it, but we can't farm it out to other countries. So security is a big problem, and I think for most of us who are writing business applications, security is probably a big question mark for all of us in one form or another, making sure that the data and our processes and all the rest of it are protected in one form or another. I would advise everybody and anybody who is dealing with data that they're passing out these days to be very careful how they do it and what they put in place to afford themselves some protection. Because particularly with the data we handle, which is medical data, if it does fall into the wrong hands, bearing in mind it's quite often personal data, albeit quite often it's depersonalized. Nevertheless, there is information in there which is highly sensitive. So then our next problem is performance and performance and performance. We'll come on to that. No surprises there. It seems to me that no matter what we do, however we speed the process up, the following day they want more. All of our customers have given us data to start us off with, and inevitably, as time has gone on and they want to go to a phase 2 pilot or phase 3 pilot, the first thing that happens is the data volumes double, triple, or increase by a factor of 10. So we're always very wary and aware of the fact that anything we do today will possibly be outdated tomorrow. And it's one of our biggest problems we're having to look at. And the final thing I'll just throw in at the bottom, and you'll be pleased to know it's not about me being sexy. The application has got to be sexy. So anybody, again, who is building their own applications for delivery to customers, these days customers expect a lot, not only in terms of functionality, but quite often in terms of how things look and feel, and whether they're seeing some of the latest on-screen gadgets being made available to them. So, let's just think now about what we're doing now to try and speed things up. This is just a simple model now of what Cosmos looks like in the background on the server. We have the same client at the front. I need 2 pointers now. We have still the same Flash client at the front end. And at the back end, we have our front end server, which contains pretty much the same My Server interface. The My Server talks to the cache controller as before, looks for work that's already been done, and it also now has a load balancer, which determines what's been asked and where best to get that request dealt with. And we now have the ability to have multiple servers, or multiple CPUs, or multiple processes running, which is illustrated over here on the right-hand side. We've got a remote procedure call running between the servers, another controller which is looking at what's been asked and what's working at the moment, what the other processes are up to. And all the various requests and inquiries are farmed out to CPUs, cores, servers, as appropriate to give the best overall response return. At the moment, we've got a single database. We haven't split the database up, which is one of the things we probably need to do in the future. Data sharding and the like to try and break the processing down even further. So we haven't done that yet. So down at the bottom here, I've got a NAS unit, network attached storage, which basically is just a large amount of hard disk space. And all the processes, all the servers share the same. And bottom left, we have the same importer receiving data as it always has done. So this has given us another performance improvement straight away in that we can now spread our load over many processes if we want to. We can have multiple people logged on at the same time, and they can all be applying and sending off requests at the same time. Where feasible, we've now started also to break the request down. So if a request is made up of 3 or 4 or 5 component parts, we can spawn each of those off to a separate core or processor, and each one can be worked on independently. The answers get returned up, parallel processing style, I guess, and goes back through to the My Server and ultimately back to the client onto their Flash display. So some of the new tools we're looking forward to be using, as what Morten was describing yesterday, was the isolates and futures, because we see that as giving us a tremendous amount of potential speed and performance improvement very easily, and possibly very low coding overhead as well, which is also important. So the overall architecture has changed quite a lot, and as I said, now we can have multiple users, we have complex inquiries, we can have large data sets, the memory is handled better, and it all works much more slickly. So some of the solutions we've adopted so far, and this slide's a little bit of a cheat, we'll come on to that. But first of all, we've had a lot of help from Dyalog thank you for that. We've spent time with them in their offices looking at some of our code and determining that, yes, it is horrible. And we've had some good improvements put through. We've had some very good speed-ups. So thank you again to Dyalog. It's been great. And to APL as well. Just purely having the ability to run things in the session and try stuff out has proved invaluable. Because bearing in mind, with the information we're receiving, we don't know very often what exactly it is or how it all really interrelates. The data formats are often a mess. The data is a mess. And so being able to just play with it in the session and get a real understanding of what it is we've got to deal with has made a huge difference to us. And I'm not sure we could have developed what we've developed so quickly with any other language, or given ourselves the flexibility that we now have with any other language. I'm sure you could have coded what we've done in other languages, but I suspect you would be bound by what you've done very much. So APL has helped us tremendously. We've started, as I've already described, caching. We've done basic caching to say, well, okay, if a request has come through we've already seen, we'll reuse it if we possibly can. And we want to take that now to a new level whereby we can actually disassemble in much more detail the request from the researcher and cache individual parts of the calculation or the request or whatever it might be that they're doing, and store on disk the results of much smaller granular inquiries. The idea being, at the end of the day, that we can then obviously just pull these things back together again to build up an answer to the bigger question much more fast, much quicker. When we started with Cosmos, we were using DCF files, and they were great, they were fine, and as we all know, with DCF files, you can just dump stuff in them and pull stuff out, and they're great. But because we have now multiple processes going on, we could see straight away that just having a DCF is not really all the answer. You don't want to be copying the same data out of files all the time and putting them into individual processes. So I know some of you are already using map files in the audience, probably to great effect. But we found that by using map files, map files, if you didn't know, are an operating system interaction. So the operating system looks after the file I/O, and it reads in what you want when you want it. It pushes back stuff back when you don't want it. So it's meant that our workspace size has come down a little bit. And more importantly, we can share the data between processes, independent processes. And the operating system basically looks after that side of things for us. So again, very useful. In itself, it hasn't provided massive performance improvements, but it has provided certainly memory improvements, and as I say, the ability to share stuff around much more easily. We have a Flash client side, as I've already described. Now, Flash is sort of going out of favor somewhat these days. People keep talking about HTML5 and all the rest of it. And we will probably, in the near future, be switching over to HTML5. We haven't done that simply because, for all of its faults, Flash is a really nice way of taking stuff off the shelf and bolting them together. And we saw yesterday with Syncfusion, with a library of tools and bits and pieces, you can very easily produce a very nice front end relatively easily. And certainly one of the tools they had, I think he said it was 300,000 lines of code. You don't want to be reinventing that every other week. So we're using Flash, and we're pulling stuff off the shelf and these modules, bolting them together to give us the interface that we need. So that's not really a performance improvement as such, but it means that we can produce the results much more quickly. This is one of my cheats. I've put in here Syncfusion. We're not actually using Syncfusion yet, but that's one of the things I think that we will be using, certainly experimenting with as we move forward into HTML5. Looking at some of the tools that were demonstrated to us yesterday, there were a number of things there, to say the least, which are going to be of great interest to us. So we're looking forward to using that and the tools and the facilities that Syncfusion give us. And yeah, we'll see. So maybe in a year's time, I'll be able to show you Cosmos with some Syncfusion things in it. Now, so getting more onto really, I suppose, the point of this talk, when we started the Cosmos system off, we did the usual APL-y thing. We made an assumption, we built the code. We didn't spend too much time thinking what was going on, really, and we just built it, made it work, and thought, yeah, great, this works fine. And as time has progressed, we've realized some of the errors of our ways. So we've had to refactor repeatedly a lot of code. Nothing new there, I suspect. But refactoring to get more performance, change the algorithms we're using, changing the approach we're taking, which depends very much on the data sets we're looking at. When we first started, a lot of the code we wrote was deliberately very general because we didn't know what we were going to be looking at. So we were, thinking to ourselves, we were being very clever here, writing code which would be or could be used in pretty much any environment with any data set at any time. That turned out to be a slight issue because generic general code is great, but it doesn't necessarily give you the best performance for a particular data set. So we're now switching to look again at our systems and our code and looking to see how we can write special cases for specific parts of the operation. And in doing that, that has generated some sizable savings. Bearing in mind the amount of data we're looking at now, we're not talking about vectors of 10 or 100 or 1,000 items. We're talking about vectors with millions, tens or even hundreds of millions of items in. So any saving we can get will make a big difference. And the cost of running a test to see whether a particular case is going to be better than another case is far, far less than the potential savings we can make. So I guess the lesson there is, don't throw away the if this, if that sort of statement out of hand, and special casing can be very valuable. So let's just look at some examples, and this is quite nice because it follows on from Eugene's talk earlier on quite nicely, I think. We have inside the system many, many vectors of information. Now, over time, this has changed. We had text, we had matrices of text items, tables, you name it. We've now got keys and indices and pointers, all sorts of mechanisms which we're using to try and speed up the system when we ask it, is this person age 65? Are these people age 65? And so forth. So if you just look at this very simplified case, we've got a drug with a code 23, simple enough. And then we've got a vector, which in this case represents 3 patients. And inside each of those vectors, we have 3 or 4 drugs, the drug codes. And typically what we want to do is to try and work out or see quickly how many drugs or what drug applies to which patients. So a simple drug equal patients algorithm works very nicely, very quickly, as Eugene was saying earlier on. And we get that result. Nothing unexpected there. Now, as a result of our refactoring and special casing, we've had a number of people working on the code. They've all got their own personal techniques and methods. And the data flowing through the system has changed. So quite often we have found ourselves rewriting a bit of code quickly to meet up with the data that is now coming. And whilst we produce an algorithm that works, it's not necessarily the best algorithm or the nicest algorithm. So we've been trying to do some tests to see what works best. So this is a very simple test routine I've been playing with actually for quite a long time, and I've been playing with it whilst we've been here as well. But essentially, the top of the function is just generating some data. It doesn't matter what the data is for the moment. Then there's a loop with, in this case, 100 iterations. Then there are some tests, 6 of them there. A check to make sure that all the tests come up with the same answer. If it doesn't, it stops. And we're using the Dyalog profile commands to run this with different sets of data to see what algorithm actually works best for us in particular scenarios. So if we look at the simple case, where I'm just looking for a number in a vector of vectors, and we look at the top half of that table, the number of vectors is constant. There's 10 vectors in this particular sample, and the number of items in each vector grows from 10 at the top through to 1,000,000 at the bottom. And you can see on the right-hand side the timings in milliseconds for running that test. And beneath it, there's another set of tests where we increase the number of vectors, and in this case, the number of items in each vector has been limited to 10. So we're going from 10 vectors to 1,000,000 vectors, where each vector has 10 items within it. And again, you can see for that simplified expression, 100 equals vec, the timings for that, running from 0.2 through to 17.5 seconds. And if we look at that on a graph, you'll see it's quite nice. These graphs aren't particularly clever, so I apologize for the poor naming. But the red line shows us the effect of increasing the number of vectors, but keeping the contents of the vectors the same. And that's nice and linear. And I have to say, I wasn't expecting that. I was expecting there to be all sorts of memory problems and issues and other attributes, artifacts coming in, which will affect that line. But bear in mind, this is a logarithmic scale. So although it's a straight line, the actual time is sort of going up through the roof quite dramatically. And if we just go back to that table, you can see we've gone from 0.2 at the bottom end of the scale to 17.5 seconds, and 0.2 and, 0.7 of a second for the changing the number of items. So at the bottom end of the scale, where we've got a few number of vectors or a few number of items, it doesn't matter a great deal. As you can imagine, we haven't got much work to do. It does it a lot quicker. At the top end of the scale, it takes a lot more time, clearly. But it's relatively linear, which is one of the things I was surprised with. So this is 100 equals vec. Very simple, very straightforward. But within our code, bearing in mind we've had lots of different people at different times fiddling and applying their own personal preferences, the same sort of algorithm can be represented in different ways. They all produce the same answer. I'm not going to argue whether which one's better or not. Some of you might say, well, why are you doing that? Well, the point is not to see why we're doing it, just to have a look and the effect of doing it. So for some people, they like to use the compose operator. That appears quite a lot in our code. It's not one I particularly like, I must admit, but others do. I'm running out of time. So anyway, I shall speed up a bit. So you can see these. Don't worry too much about the lines of code. But if we now time those, we can see there's a big difference in timing, much as Eugene was saying earlier on today. So in this particular case, as we go from 10 through to 1,000,000 vectors, we are increasing our time quite considerably, clearly. And the more straightforward algorithm, 100 equals each vec, is 18.5 seconds through to using an epsilon underbar, taking pretty much twice that. However, again, all this is on the log scale again. The timing is fairly linear between the system, which one you're using. As the data increases, the lines go up in a very controlled sort of way. If we change the number of items in the vectors, we see something slightly different. And the different algorithms have quite different timings against them. Again, this is log scale, but the top line there, as you might expect, relates to the epsilon underbar. The bottom lines to the equals type of algorithm. Down at the bottom end of the scale, with small amounts of data, it doesn't make a great deal of difference what algorithm you particularly prefer or use. So you just need to be very aware when you're doing this sort of optimization, you've got to be clear what your data is and how it looks, because if you're doing performance or trying to do performance improvements, it has a huge effect on the ultimate outcome. This is the same sort of thing again, slightly different algorithm, Scalar Across, I'm using an iota on the bottom example. This is just to force it to produce the same answer as much as anything else. And if we look at the timings on that, you can see straight away, although represented slightly differently to the previous table, as you might expect, 100 equals vec is very much faster than using a dyadic iota. And again, we can represent those on a graph. One of the things that surprised me again was that no matter which of the algorithms we used, increasing the number of vectors gave a very linear response. Increasing the items in the vectors was slightly different. And of course, at the top end of the scale, then you start getting other attributes going on, things like workspace full, for example. This one here is slightly more interesting, maybe. Very straightforward. We have a lot of this going on, a lot of Booleans in the system. So we have create a Boolean vector, 1 million items, and we want to index into that Boolean and assign it 1. And we can do the same thing with a simple integer vector as well. And if we look at the timings on that, you'll see, and this surprised me in actual fact, that the indexing into a Boolean was much slower than indexing into an integer. I'm sure there are all sorts of reasons to do with handling Booleans, but just be aware, really, that the fact it's a Boolean does not automatically mean it's going to be faster. And again, if we draw that graph, at the bottom end, as you might expect, there's little or no difference, but that difference grows quite considerably as we go forward. And this is one other thing which surprised me. I was absolutely certain that to do Boolean equals 0 was going to be faster than a Boolean less than 1. So I religiously went through making sure that the code never said Boolean less than 1 or less than or equal to 0 for that matter. And then I thought, well, I better just try it out and see what happens with the first timings. And to my surprise, even going to 10 million items, they were all the same. So I suspect somebody, not a million miles away, has been optimizing those sort of things. Okay, so what? The generalization and special casing we've done has given us something like a 10 times speed up compared to where we were. But you do need to be very aware of your data. Always consider and reconsider what it is you're looking at and why. Caching has given us a huge improvement as well, but obviously that does depend on what people are asking for. And memory mapped files. Better memory handling, data shared across processes, which is the main improvement really for us, and a small but useful speed improvement. And just to put all that into some sort of context, when we started with our version 1, we had up to, at one point, 20 million records being dealt with. And a typical sort of analysis was 15 minutes. We were using DCF files, generalized code, and integer pointers. Version 2, where we put the map files and Boolean masks in, speeded that up to 3 minutes, but it also increased the number of records we could look at by doubled it, really. Version 3, we jumped to 150 million records, and we have managed to get the inquiry time down to 45 seconds. And the very latest version, which we were looking at briefly today, where we have the processes spawned over different cores and different CPUs, we can now deal with greater than 300 million records. And a typical inquiry time, turnaround time between the client and the server is circa 30 seconds. Now, for some people, that doesn't sound a huge speed. 30 seconds hitting the button and waiting 30 seconds is a long time, and it is a long time. But the system is doing a tremendous amount of work. And to put it into context, when we were demonstrating to Pfizer, I think it was, a few weeks ago, the chief IT person, whatever they called themselves, said that in the 15-minute demonstration that he managed to see, we had managed to do what they were previously taking 2 weeks to do. So it just goes to show there is, the power of what it is we can do with APL over more traditional SQL-type databases with federated data architectures. So that's really it, in summary. Thank you for listening. Any questions?
Can you tell me about the hardware side of it?
Yeah.
Are you using Linux boxes? Or
No, we're using all Windows servers and we're using middle-of-the-range servers. We're deliberately not going for the top-end equipment at the moment. We're sticking to, in the cases at the moment for our test database and systems, is running an 8-core AMD chip with about 65 gig of RAM.
So when you have independent processes running on the same box, do you run into memory contention between those processes? Does memory become a bottleneck, the way the hardware deals with it?
It certainly can be, yes. And that's an area where we have to think about moving the inquiry off to alternative cores, not cores, CPUs, or even servers. But at the moment, we're managing to keep it under control on a single chip.
And in one of your slides, you were showing, do you have like a relational data store somewhere in there? And are you mapping directly to the network attached storage?
At the moment, we're going directly to a network-attached storage, and it's a single store. Our next phase is to start sharding the data and breaking it up into individual pieces, and then sharing that around to different locations.
Thank you.
This is more of a caution than anything else. Seeing the integer versus Boolean index design example, looking at those things and doing micro optimizations based on a micro-analysis are misleading and dangerous.
They are.
Because you can get things like, well, suppose I wanted to put that array on a file somewhere. It would take 8 times as long or more or 32 times as long to write the integer version.
Yes, absolutely right.
Doing a plus reduce, that can be done a word at a time in the Boolean case, but the other one has got to do it. So it's important to look at the bigger picture when you're
Absolutely. I couldn't agree more. I've been taking a very simplistic view of this, but you need to be very aware of your data and what's going on in the background. And this is where help from Dyalog has been very useful to us, because they can warn us away from doing certain things or making poor assumptions. Yeah.
Paul, just a curiosity, did you investigate the idea of pre-processing certain queries and storing the results as a Boolean? In other words, say a drug by patient array that you then refer to rather than going back to the database?
Yes, we do. There's a number of things we do. So as part of the import process, we create axes. So for example, we might take weight and height and create body mass. Or we might preempt the fact that there's a particular style of question that could be asked. And if we think there's a strong enough argument for that, we will pre-build that axis into the data. So yes, we do. Thank you very much for listening.